So we're thrilled to have Matthew give us the seminar on this continuous translations. All of you know Professor Seiberg, great eminent physicist who's visiting us from yesterday. He'll be here today and tomorrow. On Thursday, he's like that. Please take this opportunity to meet him, to ask him all your questions.
Thank you. It's a pleasure to be here. Thank you for the invitation. Before I start, the talk has a funny structure. There's a kind of regular talk, which is less than an hour. I encourage you to ask lots of questions throughout. And then the second part of the talk, these are various, if you wish, appendices or add-on material, which can go for another hour, depending on how many questions. I'm not going to go another hour. I'll probably ask you which of these topics you would like to hear about, and then we'll take it from there. This will also be driven by questions that will be asked throughout the talk. So please interrupt me with questions. The other comment I would like to make at the beginning is that you can see here at the bottom, I'm part of this Simon's collaboration, Ultra Quantum Matter, which put together people with field theory background, but mostly condensed matter people. These are the members of the collaboration. And I personally found that enormously inspiring. And I feel that there's room for more interaction between field theorists and condensed matter physicists. And I think that people from both disciplines can learn from each other. And such a collaboration, I'm sure, will be fruitful. And given that there are people here in the audience from these disciplines, my first comment is interact with each other. I'm sure you can learn something from each other, and that would be useful. So let me start with the talk. I'll start with a bunch of models so that you know what I'm talking about, and then I'll get into more details. So we'll discuss a certain continuum quantum field theories. I'll define exactly what the class is. It would be a very large class. A lot of the members of the class of models are models that people have been interested in, but they were not kind of lumped together in the same way. I'll present it from several different points of view. Some people would prefer one point of view rather than the other. So these are some examples. U1 gauge theories with constant charge density. So we add to the Lagrangian the term linear with AT being the time component of the gauge field. So the equation of motion of AT, which usually leads to Gauss' law, says there is a constant on the right-hand side, rho. So this is a system where you constrain the charge density, not the total charge, but the charge density. And then there would be some nonlinear sigma models with a term with a single time derivative. An example would be the continuum Lagrangian for a ferromagnet. I don't know how many of you know what a ferromagnet is, and of them, how many of them know that this Lagrangian describes a ferromagnet? This is something that is almost a century old, well, half a century. So Z is a complex field, and there is a term which is first order in time derivatives. I'll discuss it in more detail later. So these are nice continuum Lagrangians that people have analyzed. So this is not the first time these models are analyzed, and there are many other models in this class of models, in this class. And the novelty in this discussion is that we'll pursue a line of research that I've been pursuing for more than a decade now, is understanding systems by using their symmetries and the anomalies in their symmetries. Now, interacting with people in condensed matter physics and in field theory, I know that they're thinking about anomalies completely differently. So I try to get everybody on the same page in the coming slides so that we all know what we're talking about. And so I'm going to start with a very brief introduction, toy model for the model with anomalies. And the terms that people use is the 't Hooft anomalies and Adler-Bell-Jackiw or ABJ anomalies. This is the high energy terminology. And I'll demonstrate it in the model that every single person in the room knows, because you studied that in school. So people always think that anomalies are something very fancy, very complicated, very modern, and high energy physicists think it is associated with some divergences in how you regularize the functional integral and fermions and this and that. And condensed matter people think that because we are on the boundary of an SPT phase, and there's something very modern and subtle in the SPT phase that gives you something. Does anybody here know what an SPT phase is? Just want to know that. Yeah, at least one person. Okay. So I'll show that. I'll give a really down-to-earth example, which will actually be helpful in the rest of the talk. So consider a classical particle on a two torus with periodic boundary conditions with a constant magnetic field. This is something that you learn when you're an undergrad. I'm doing classical physics. So this is the classical Lagrangian. So we have velocity square, and then there's a coupling due to the magnetic field. And since x1 is periodic, it's periodically identified, the Lagrangian is not single valued if I shift x1 by L1. So the Lagrangian is not globally well defined, and is not translation invariant. Translation, I mean in the target space in x1 and x2. So this way of writing it, it's not invariant under translations of x1. If you are a little bit more sophisticated, you see it's also not invariant under x2, but let's put that aside for the moment. However, when we look at the equations of motion, these are the equations of motion, they're perfectly well defined. So the fact that this term is not globally well defined does not matter when we look at the equations of motion. The equations of motion are invariant under these identifications. Also, the equations of motion have a U1 times U1 symmetry, shifting x1 or x2 by constants. So the classical Lagrangian is well defined. If we are classical physicists, we could just say that we are interested in these equations of motion. So from 19th century physicists, we have an equation of motion with acceleration and velocity, and I think it's called Lorentz force. And it's perfectly well defined, and it is translation invariant. There's a U1 times U1, and it's U1 rather than R because of the identifications of the x's.
The action defined standard boundary.
No, no. The action is not well defined.
Boundary condition. I should x1 to play with
But the total derivative does not integrate to zero. And you can add surface term to make it integrate to zero. I will not do it that way. I'll do it some other way. There is a surface term for maps from the torus, from time. The torus is the target space. Torus is the target space. The surface term is a surface term in time. And the surface term in time does not integrate to zero for configurations which wind around the Euclidean time direction. This is this is 19th century physics. So let me move to the 20th century, where Landau studied this problem. And now comes your question. So the action is also not well defined. But what we do need to define is not the action, but the exponential of the action. This is very common, except that here we're doing it in a really elementary down-to-earth problem. And the proper way to define this action is actually quite subtle and quite complicated. And the branch of math that is needed is differential cohomology. And to quantize this system properly, we need something called pre-quantization. But I'm not going to do it here. Yeah. We'll soon get to it. That's the next thing, but a very good question. But so far, I just said that something needs to be done, right? As it stands, it's not well defined, and we need to define more carefully what we mean.
So, but the simple way would be if I divided the torus into two parts and defined a non-trivial map between the two.
Yeah, that's a way to define. One way to define it is to say, you say that there's a non-trivial bundle when you want to trivialize the bundle and have transition functions between them. And there is a way to do that. And then you can define the action by saying that in the patch, you write this, but you need a correction term when you go from patch to patch. And all the stuff I'll be talking about in this lecture is about this correction term. So I said earlier in the talk that I wrote two papers on the subject. In paper one, I took approach number one. But then I realized that physicists do not like this approach because it's kind of too abstract. And mathematicians do not like this approach because it's too concrete. So I wrote a second paper deriving the same result using a totally different method. Where mathematicians do not like when you make choices. You should be able to define everything without picking a local trivialization, etc.
Sorry to repeat, but can't I define a theory with periodic x1 and x2 on the torus?
You can.
Then for that theory, then I'm not allowing winding.
No, if you're not allowing winding, if you're not allowing periodic boundary conditions of the x's, that means that you're not on the torus.
That's right.
So that's a different problem. There's a problem on the plane. You can be on the plane. X1 and X2 are real numbers, and then
the actual time, so it's periodic time, but it's the actual
okay. So to define when you discuss this path integral, it's better to think of t as being Euclidean compact time.
okay.
But if you look at the, that's correct. But you still have to think about them. They are instantons. Even instantons have implications even in Lorentzian signature. So we can go from. So we have to define it carefully, and I'll just give you the answer that all of you know. In fact, somebody already, I think you pointed it out. I think it was you, that B has to be quantized. So when you define it carefully, the magnetic field has to be quantized, because otherwise the thing doesn't make sense. So when I was asked, is the action meaningful? For generic B, even the exponential of the action is not meaningful. Only the B has to be quantized. But what's more interesting for us, and surprisingly fewer people know, but it is already in the old literature, which is a century ago, that this problem is not translation invariant in the quantum theory. And the way to see that is that the quantum theory depends not only on the magnetic field B, but also on the Wilson line or holonomy, the integral of A, the Aharonov-Bohm phase as you go around the. So there's more information in specifying the problem. The information is not just the magnetic field, but also the Wilson line. And the Wilson line necessarily depends both on x1 and x2. The fact that it depends on x1 is obvious from this thing, right? We use a gauge where A2 is linear in x1, so the exponential of the integral of A2 is oscillatory in x1. So these objects, before we get into any details, are oscillatory in x1 and x2, and the problem as it stands is not translation invariant. In fact, we know how to quantize the system. We know the answer. This particle in the magnetic field has k states, k being the total flux, and translations in x and translation in y are discrete, and they satisfy clock and shift algebra. So we don't have continuous translation in this problem. So the classical Lagrangian is ill-defined. The classical equations of motion are translation invariant, but the quantum theory is not. And we can say, I've already said that.
When you said k states, you meant in the lowest Landau level.
In the lowest Landau level, but also in the 17th Landau level, there are k states, and they satisfy the same algebra.
Right.
So already in every level, or in fact, the full Hilbert space does not have U1 times U1 translation symmetry. The symmetry is ZK times ZK, as I write here. And so the symmetry is broken to that. And as I say later, as I will soon see, the symmetry is realized projectively. And relatedly, because x1 and x2 are periodic, we can add theta terms to the Lagrangian. We can add theta 1 and theta 2, and we can shift theta 1 and theta 2 by shifting x. So when we shift x1 by a constant or x2 by a constant, this has the effect of shifting theta 1 and theta 2 by a constant. Because, right, the Lagrangian had x1, x2 dot. So if I shift x1 by a little bit, it shifts theta 2 by a constant. So from this way of saying it, the problem depends on two more parameters, which are not there classically, theta 1 and theta 2. These are these winding around Euclidean space. These are the standard theta parameters that exist in many problems. And interestingly, they don't have a preferred zero. You can't say, oh, why did you turn it on? I prefer not to turn that thing on. Well, there's no preferred point, which would be called zero. So to specify the problem, I need to specify an origin on the torus. What I mean, yeah.
And just to understand the zk times zk, I'm thinking of this way, please tell me, okay? So x1 and x2 satisfy this commutation relation, which is x1 commuted x2 is 1 over k, something like that.
Yeah.
2 pi by k. And but x1 is also periodic. So
Yeah.
the really good variable is not x1, but e to the power I x1.
Yeah.
And then you get the clock and shift.
Yeah. That will be on the next slide.
Okay.
So the only thing which is perhaps new here is that I interpret that as an Adler-Bell-Jackiw anomaly. So this is something that just one second, that Landau already knew in the 30s, and I'm going to interpret that as an Adler-Bell-Jackiw anomaly in a very anachronistic way, because that was in the 60s. What was the question?
Just like the Simons here for the mapping speakers, like x1 and x2 will be discrete. That's why you're saying.
They are not discrete. They are operators. They are classically, they are numbers, continuous numbers. Quantum mechanically, they are operators. And in fact, you cannot even diagonalize both of them because they don't commute with each other. What you meant to say is that e to the I x1 has, once you diagonalize it, it can have discrete eigenvalues. But saying that it's in Chern-Simons, I can give you far more sophisticated. This is quantum mechanics that was solved in the 30s, right? Chern was alive. I'm doubtful where Simons was alive at that point. This is really much more elementary. And I'm going to interpret that as an Adler-Bell-Jackiw anomaly in a way that will soon be clear. So the point is that people who know about the ABJ anomaly will soon recognize that that's what's going on here. And the people who don't, you can use that as the definition of the ABJ anomaly. So this is related to questions that people ask. If there is a symmetry, originally we had U1 times U1, there are charges. They're conserved charges. And if we just apply an hetero procedure or whatever, we find these two charges and we look at the equations of motion, these charges are conserved. d by dt of P1 and d by dt of P2 are 0. However, P1 and P2 are not well defined because if I shift x1 or x2 by a constant, there is a piece here which is not well defined. This is related to comments that people made. However, I can also study these charges. These charges are well defined, P tilde, but they are not conserved. And anybody who studied the ABJ anomaly is familiar with the fact that we have two currents or two charges. One of them is conserved but not well defined. The other is well defined but not conserved. And then we can form things that do make sense. We take the charge which is conserved but not well defined, say P1 or P2, and we exponentiate it with just the right coefficient such that it does make sense. So when we have an x2 here, we design the coefficient here such that when we shift x2 by L2, this thing is periodic. And these two operators, T1 and T2, satisfy zk times zk symmetry. So this is also common in ABJ anomaly. It's kind of these. In ABJ anomaly, it's much more subtle. There's a continuous symmetry and it's a chiral symmetry and there are divergences. You need to regularize and this and that. But there is a global symmetry and it's violated in the quantum theory. And what is preserved is a discrete subgroup of it. That's what we see here.
And if we were restricted to the lowest Landau level, that P1 by K is same as x2.
That's correct. That's correct. On the first Landau level, then the problem simplifies. But this algebra is true for the entire Hilbert space. And this algebra is realized projectively. Again, this is not something new. It was first pointed out by von Neumann in a paper by, it was first pointed out in a footnote in a paper by von Neumann and Wigner, and later elaborated on by Wigner, that in the quantum theory, the classical symmetries, if they're there, they didn't say that if they're there, but if they're there, they could be realized projectively. And in modern terms, we refer to that as the 't Hooft anomaly. And the 't Hooft anomaly should be the same at low energies and high energies. The 't Hooft anomaly in this case is this projective phase. And this is the statement that we should have this phase for the entire Hilbert space, both in the first Landau level, as Shiraz wanted, But that's actually true for the entire Hilbert space. So we can find this phase in the UV or at short distances or at high energies, and then get constrained that the same phase should also be there in the lowest Landau level. In modern terms, this is a 't Hooft anomaly batching. We find the phase in the original problem, and now we can take this Hamiltonian and add terms. As long as we preserve the symmetry, the phase is still there. Might not be so easy to solve, but we still know that there should be this k-fold degeneracy because this algebra should still be there. So to summarize that, the take-home lesson from that is that, first of all, this is a system that you have all learned very well, you know very well, you know how to solve it many different ways, but it has a classical symmetry, which is not there in the quantum theory. And for me, this is the definition of ABJ anomaly. The classical system has a symmetry, which the quantum theory does not have. And notice, you don't need the bulk or SPT or divergences or fermions and how you regularize and the measure in the functional integral. All these things are totally irrelevant. Just thinking carefully of what the distinction between the classical and the quantum theory and this thing comes about.
Thank you. So in the classical theory, first there were two U1s.
Yeah.
First, it's broken down to two ZKs.
Yeah.
Second, they don't compute. So both
That's
aspects.
correct. The second aspect in this case so when the fact that it's broken to two ZKs, that's the ABJ anomaly. The fact that they don't commute is they do commute on operators because the commutator is a C number. So it does not commute on states. They do commute on operators. That means that the symmetry is realized projectively. The symmetry is still ZK times ZK, but it's realized projectively on the Hilbert space. The way it acts on operators, they commute because it's a C number. This distinction will soon be important. Okay, that was the easy part of the talk to get everybody relaxed. And at least nobody criticized what I said. And so now let's discuss the models. I just copied the slide again. These are the models that we'll discuss. And unlike the anomaly that we have seen so far, which was...
Sorry. Often in field theory, when we look at anomalies, we compute them using a loop diagram. Is there some fake loop diagram you can compute that?
The thing that you really compute is the exponential of the action. And the loop diagram is kind of a prefactor in the exponential of the action. In this case, it's all quadratic, so there isn't much to this model is solvable, you know. You can write the full wave functions and everything in complete general.
Analog of the triangle diagram.
There is no analog of the triangle diagram. No, that's the beauty of this example. And that's what it will be so easy for me to generalize it, because the story is not about the triangle diagram. The triangle diagram is an example of how this thing can happen. It can also happen other ways. In fact, you know that in 1+1 dimensions, you know that the anomaly first found by Schwinger is a bubble diagram. That's when you have fermions. If you bosonize it, you see it at tree level. Yeah, that's what I had here. So the time derivative of this, is 0. And the time derivative of this is b times x2 dot. So the time derivative of, so the thing on the right-hand side of the conservation. So these charges are well defined, but the time derivative is not 0. The time derivative is an operator. That's the thing that this is a very degenerate system. You're not going to get the full-fledged story here, but yeah, this system is extremely. I gave you the shortened version. I have a 3 times longer version of it, which demonstrates more physics you can extract out of this system, how you gauge systems and what happens under gauging, etc. But I'm not going to do it here, even if you ask.
But having written it down.
Yes. It appears, this story with a lot more details, as it said, it appears in an appendix in my latest paper. So there's an appendix at the end with the title, what was it? Something like an anomalous view of a particle in the magnetic field or something like that. So it's all spelled out in a lot more details. So this was kind of mostly as a pedagogical thing because there isn't a single, so far I have not presented any new result. I have not said anything that Landau did not know. So it's not that somebody, 5 years ago did the same thing. The credit. So, okay, so these are the models. So now we're going to apply the same reasoning to all these more interesting models. And all these models have some common features, which also exist in the toy model that I've just described. And the classical Lagrangian is not well defined. That's this is the first thing that tells you that you should watch out. But the equations of motion are well defined. So the classical physicist who knows about the equations of motion said there's no problem, and they are translation invariant. And I should emphasize that the translation I had so far was translation in the target space, because x1 and x2 were the target space of the quantum mechanics. Whereas here I'll talk about translations in position space. And different fields have different name to, some people call it real space, and some people call it the base. So in all these models, the quantum theory, we need to define the exponential of the action. That's what we also had in the toy model, or its Euclidean version. And we do that such that the equations of motion are unchanged. However, when we try to define the exponential of the action in the quantum theory, there's a few subtleties that usually arise. First of all, some coefficients should be quantized. We've seen that already in the example we saw with the particle in the magnetic field. This B had to be quantized to make it well defined. And related, sometimes it's related to that, we also have additional parameters that are not there in the classical theory, like theta parameters. Theta parameters appear in the quantum theory, they are not there classically. And we saw that in the magnetic field, which can be thought of as a choice of origin of the torus. So translation was broken, and you could say classically it was translation invariant. So how was it broken? Well, we had to choose a point. Say, this is what we mean by zero. So the symmetries. So we need, there's additional data. And in our case, which I'll elaborate on in the following slides, this data that we need to add explicitly breaks the translation symmetry to a discrete symmetry. So this is very similar to what we saw in the particle in the magnetic field, except that there it was in the target space, and now it would be in position space, in space itself. And also we'll see that the discrete translation symmetry is extended. In the example of the quantum particle, it was a central extension. The extension was central, it was a phase, and it was the same phase for the entire Hilbert space. What we will see here is that not only is the symmetry discrete, the extension is not central. And what we have there is an operator. There's an operator setting there. So the algebra is not only a subgroup, because it's discrete, it's also extended completely in a non-central extension. And many of the results I'll present are known in one form or another over the last few years. Some of them go back maybe 40 years. But the interpretation was very confusing. And there has been a lot of this controversy in the literature about what they mean. And I'll present a unified view on all of these problems. And I'm not going to explain all the controversy that people had. I'll just present the right answer. But I can assure you that it resolves all the confusions that these papers had. And I'm not surprised there were confusions and controversy, because as you can see, it's quite subtle. And I think that the way I present it kind of cuts through all the confusions. And the main new point is to really separate what's classical and what's quantum, and what we mean by the quantum theory. That's where, and to really work in finite volume, because as we will soon see, the infinite volume limit is quite subtle. So we'll present a unified treatment using an ABJ anomaly in translation, and I sold it like here, ABJ-like, because it's unlike the ordinary ABJ. It's not in an internal symmetry, but in space symmetry. So this is my notation. Space will always be a flat torus. I'll work in D dimensions with the volume V. I'll switch back and forth between Lorentzian time and Euclidean time and use mu as a general index. This is standard notation so that I don't have to repeat it every time. And let's start with the first example. This problem of U1 gauge theory in 1+1 was first analyzed in 1+1 dimension in 1979 by Fischler, Kogut, and Susskind. So they were interested in the Schwinger model with constant charge density. not constant charge, but constant charge density. And they found many peculiarities. And this paper was somehow dormant for many years until Max Metlitsky, who was a master student at the time, picked it up. And he really clarified a lot of the confusion. And I'll elaborate on what he did. I'll do it in more generality and also extend it in various ways. And since then, various people mentioned it, but I found a lot of the results there, but it would not be the presentation that I will have here. So again, this is the Lagrangian. And the classical equations of motion are gauge invariant, because we differentiate with respect to AT. Gauss' law tells us that there's constant charge density. And now we go to the quantum theory. And what is obvious, and many people said, that in the quantum theory, this coefficient rho has to be quantized. And the easiest way to do that is we go to Euclidean signature, and then we let the gauge transformation for AT that winds around Euclidean time. And therefore, we should have a quantized coefficient there. Another way of seeing it is that if rho is the charge density and V is the volume, the total charge, because we work in finite volume, is a finite number K, and that should better be quantized. So that gives the same answer. One is from a more Lorentzian point of view, the other is from a more Euclidean point of view. D. D is the number of space dimensions. I keep it arbitrary. As you will soon see, the physics is completely different in different number of dimensions. Okay, so this is the total charge. And the fact that there is a coefficient which is quantized in the Lagrangian, we are used to that by now. But what's peculiar here is that the Lagrangian density depends explicitly on the total volume. That's a little bit unusual. It's the first telltale that something subtle is going to happen, because you could ask what's going to happen in the infinite volume limit. And then the answer is depend. Well, you said V to infinity, what do you said K to infinity also or not, at fixed ratio, not at fixed ratio. There are various limits. In order not to be confused, I'll stick to finite volume. And whenever I give these talks, people always say, but what about infinite volume? And my response has always been, it's subtle enough in finite volume. It's getting even more subtle when we go to infinite volume. So let's do it in steps. If I have time, which I don't think I will have at this rate, the infinite volume limit will be discussed. So naively, the quantum theory is gauge invariant and has continuous translation symmetry, but in fact, that's not the case. So many people have analyzed this problem in various contexts. They said, okay, in order to make it well-defined, we need to quantize rho as such, and then everything is nice and gauge invariant. There's nothing to worry about. And the answer is no. This problem is more subtle. And not only should the action be defined more carefully, it's not translation invariant, which is a bit surprising because there's no explicit X dependence here. But this system is not translation invariant. So this is what we need to define the action. And as I said, the proper way to define it uses differential cohomology, or as was suggested here, using patches and transition functions between them. And that's what I did in my first paper. But instead, I'll present here another derivation of the same fact using facts that most of you know. So, which you know the fact, but in the way you know the way these facts are derived is using differential cohomology. But since you already know the fact, I'll just copy the fact that you know. So this is the fact you can cover space-time with patches and then define the action that way with appropriate correction terms. Many physicists have seen that in various contexts. But we'll take another approach. And the other approach will be the following. Let us first set K to 0. So there's no background charge. There's no charge density constraint. And then the theory has a magnetic symmetry. Magnetic in the sense that the conserved current. So in modern terms, this is a D-2 form symmetry. But you could just say that the field strength is a conserved current, because D of the field strength is 0. This is one of Maxwell's equations. And even for D equals 1, in one dimension, we can think of it as a -1 form symmetry. I don't have to use this terminology, which seems overkill. But you will soon see that even in 1 + 1 dimensions, the formulas I'm writing make sense. So we have a current. And the modern view on symmetries is that whenever you have a global symmetry, you should couple it to background fields, not to be confused with the dynamical gauge field, which I denote by little a, the background gauge field is denoted by uppercase A. And the theory should be viewed not just in isolation for A equals 0, but it should be viewed as a family of theories labeled by all possible big A that we can turn on. Right? It's a member of a much larger class because the theory should be viewed as a function of all the background fields. So let's take an example. Imagine we are in one dimension, 1 plus 1. Then we can turn on a theta parameter. In 2 plus 1, we can couple big A to little a, and yeah.
So is D space or space time?
D is the number of space dimensions. D is the number of space dimensions, and yeah, which you can see. This is what, when I grew up until a few years ago, I would refer to that as 2 dimensions and refer to that as 3 dimensions. But over the last few years, this was a real breakthrough. I've started using the terminology that the first is in 1 plus 1 dimensions and the other is in 2 plus 1 dimension, because this really avoids the ambiguity. So I really prefer this language of 1. It's a little bit more awkward, but it allows to communicate less ambiguously.
Right, so forms add up to D plus 1.
That's correct. So, for example, this is a problem that Shiraz analyzed in a lot of models in 2 plus 1 dimensions, where you can couple the background gauge field to dA. And if you had a duality between one model or another, in the dual frame, it was an ordinary U1 symmetry. And on the other side of the duality, you have a coupling like that. And in higher dimensions, it's a higher form symmetry. So this is what we would like to discuss. This is our coupling. And this is a Chern-Simons coupling. And again, it's the same story. It has to be defined carefully. The action is not well defined. And then what we really need to define is e to the I times the action. And then there are 2 ways of writing it. This is an off-diagonal Chern-Simons term. Either we get large A, D little a, or little a, D large a, and the dot, dot, dot of various correction terms that are needed to make it well defined. Now, one might say that going from here to here, this is just integration by parts. And in this form, this object is independent of shifting little a by a constant. And in this form, it's independent of shifting big A by a constant. And since they are equal, the final answer is independent of shifting either one. But that's not true. That's not true because of the ellipses here. The terms in the ellipses depend on the 0 mode of little a and big A in such a way that it depends on both. And this is very common. People who study Chern-Simons theory, you are not just allowed to end by a constant. That does not change the classical equations of motion, but in the quantum theory, it makes a difference. And this is very similar to the example I had earlier with the magnetic field, that we have explicit A dependence. It's not well defined. We can ask what happens when we change it. So now we're instructed to study the problem in every background field. Let's put a constant magnetic field. This is a magnetic field for the background magnetic field, not for the dynamical field. So in the language that some people are more familiar with, so we have particles in the magnetic field. We don't think of the magnetic field as being dynamical. We're not doing QED. The magnetic field is prescribed. And there are particles and they interact with each other. And there's a U1 symmetry, which is number of particles. And we can put background magnetic field for the gauge field of that U1 symmetry. This is extremely common. So this is the background magnetic field that I'm going to study. And in 1 plus 1 dimensions, this is the same as saying that d theta is dx, or in other words, I consider theta that is linear in x. So I take the particle with the theta parameter, the field with the theta parameter, which is a circle valued, and I let theta be linear in x. So it's not that crazy, right? I have a system with a theta parameter. Theta might depend on x, and since theta is circle valued, the coefficient of the term linear in x must be quantized so that when I go around, theta does not come back to itself, but at least comes back to itself out to a multiple of 2 pi. And in 2 plus 1 dimensions, we have constant magnetic fields, and in higher dimensions, it's a higher form gauge field. So what am I saying here? I say I have a system which has dynamical gauge field little a. Because of that, I can couple it to a classical background field big A, And I'm going to study that background gauge field in a case where it's constant magnetic field for that. So it's completely straightforward and natural. And then we find our term, because the little a, the big A, is the term linear in AT. So I've recast the problem of how to define the right-hand side here, which I said that has to be defined carefully. Says, well, it's the same as defining this one carefully, but that has already been solved. So I'm going to copy the answer from there. So we need.
Sorry, because capital A was a d-1 form field strength, the magnetic field of that is very natural object because it's d-dimensional.
That's correct. Yeah, and I take it to be a constant.
Sorry?
And I take it to be a constant in space.
Yeah. It's very
More precisely proportional to the volume form.
volume.
Yeah. And if I do that, then I did get something that is linear in A sub t, in the dynamical A sub t. So it looks like a very awkward thing. We wanted to define A sub t. So let's first not, the integral of A sub t, let's set the coefficient to 0. Then I embed it in a much bigger problem, which can be coupled to big A. And then I take this A to be the constant magnetic field, and then I have the answer. So it's a very roundabout way of defining it. But the advantage here is that here I don't need the subtle, the fancy things. I just can copy answers that I know. In fact, many people know. So when this thing is properly well defined here in Euclidean signature, if I shift xi by a constant, the Chern-Simons term is shifted by a term proportional to the field strength. It's not surprising because if you think of it in the example in 1 + 1 dimension, I said that what I have here is, so let's specialize to 1 + 1 dimension. We had theta linear in x. So if I integrate by parts, I get A sub t. But the fact that it depends explicitly on x means that if I perform translation, it's not translation invariant. Or another way of saying it, this big A, in order to get constant field strength, must depend on x explicitly. We've seen that already in the first example of the particle in the magnetic field, that physics depends explicitly on x. It's not just it's not translation invariant. So the fact that big A depends explicitly on x makes the final answer depend explicitly on x. So this is part of the action, and the action, despite appearance, is not translation invariance. And all this does not affect the classical equations of motion, and therefore does not affect the classical theory. So a classical physicist, even the classical physicist who gets up to here says, okay, so the action was shifted by that, but that's a total derivative, and therefore I don't care. But the quantum physicist knows better, this total derivative makes a difference. It's like shifting the theta parameter of the theory. So the subtlety in the quantum theory is with the action, not with the quantum loops. This is the same thing that somebody asked me before. Is there a triangle diagram? I didn't compute any diagram, but it's still in the quantum theory. It's not classical. And that's one of the reasons there has been a lot of confusion here. So what we see that the classical theory does not have a continuous U1 to the D symmetry. So classically, we could shift x1, x2, x3 by arbitrary constant, but that's not true in the quantum theory. And instead, since this object here is quantized, this two-dimensional integral is quantized, each U1 is broken to zk, where k being the coefficient in front of the Lagrangian. And I interpret that as an Adler-Bell-Jackiw anomaly in translation. So we had a classical symmetry, which is not there in the quantum theory. It's explicit breaking, not spontaneous breaking. That's also very important. So somebody could say, we thought we were in the continuum, but in fact, we have a lattice. That's not what's going on here. For one thing, the theory is still in the continuum. We can still study correlation functions at any position, not only at the lattice sites. Second, when the crystal is found, we also have a system that is translation invariant, but then we have a crystal is formed, but that is spontaneous breaking of translation. It's not explicit breaking. And the hallmark of that is that they are phonons, the Goldstone bosons of translation. This is explicit breaking. This is explicit breaking, not spontaneous breaking. And that is the statement that the quantum theory depends on more parameters. The classical theory does not, and these parameters break the symmetry. For the particle physicist in the audience, I would say this is the same way as the U1 in QCD, when it's spontaneously broken but does not lead to a Goldstone boson, the eta prime has a mass. And the mass of the eta prime tells us that there is no Goldstone boson. And this is closely related to the fact that there's a new parameter theta. And when we perform the symmetry transformation, which what we think is the symmetry transformation, theta is shifted and telling us that the symmetry is explicitly broken. The same thing is true here. We have continuous translations in the classical action, but the symmetry is explicitly broken.
Just to check, so you started by saying constant charge density, and now this is a reinterpretation. Constant charge density could be regarded as the same as coupling to a B field for this capital A.
That's correct. And the B field for the classical A, which could be a higher form,
yes.
This B field depends on the big A, and big A depends explicitly on X, and therefore the symmetry is explicitly
so
broken.
You see it very clearly in that way.
Right. This is a way of getting it. You can get the same answer in my first paper. I derived the same answer in a totally different way,
yes.
But it's the same answer. So fortunately, that's why I published the paper. Otherwise, I would have withdrawn the first one. So this is the phenomenon. Yeah.
Instead of the torus, we were on the sphere.
Excellent question. So what happens on the sphere? On the sphere, the symmetry is not broken. The symmetry is not translation, but it's rotation of the sphere. There's an SO3 symmetry. And what this thing does is to say that the angular momentum is going up by K, like a particle in the magnetic field, because I put constant magnetic field through the sphere, and that shifts the angular momentum to start at K. This is another elementary problem in quantum mechanics. The same thing is true here, but we do not have explicit breaking of translation symmetry. That's another way. Sorry? That's right. But this is another sign that the phenomenon that happens here is not that the crystal is formed. Right? It's not that the crystal is formed. Instead, what happens is just the symmetry is broken. There is no crystal. Because on the sphere, this does not happen. Sorry? That's correct. I need a that's correct. And you can see that from the equation. You need to activate this. So T is in the time direction. So I need a cycle, a 2 cycle for F to activate it, which involves a cycle in space and time to activate the effect. But the effect is there. So there's still subtleties on the sphere if I have this constant charge density, but it's not translation symmetry.
Say this, but just to internalize it, if I thought of it as rho times the volume, it seems completely translationally invariant. Then you wrote it in terms of dx1, which there's
No, I did not say rho. The coefficient is rho times the volume.
Right.
The coefficient is rho times a sub t. I need to define what I mean by a sub t.
Yeah.
All right, so you wanted me before, I think you asked me about using patches. So when you want to write a sub t, you need, first of all, patches around Euclidean time because it could whine. But that's not good enough. That might not be good enough because you might also need patches as you go around space. And as you go around space, you need patches there to sew things together. And that depends on where you put the transition function. So that in different ways of seeing it, you can put this dependence on X in different places. And I can give a whole lecture on every single one of them. Look, it took me a while to get to this interpretation, but all of them lead to the same. In
the first example, just particular magnetic field, you had these U and V matrices, and the shifting of the origin was phasing these matrices. That right, just adding a constant phase. There was no actual choice for that phase.
That was a question?
No.
And how should I respond to a question that does not have a question mark?
Say yes.
Yes. And furthermore, you can do the algebra here. It's a little bit more work. If you do it twice, they don't commute. So translation, so first of all, we got only discrete translations with this TI by a particular amount. But furthermore, these translations don't commute. And performing this transformation in X and then in Y or in the other order, we get an exponential factor here, but the exponential factor is an operator, not a C number. So the algebra is extended. So that's not an 't Hooft anomaly. This is unlike the particle in the magnetic field. intuitively, if we have constant charge and we have this background magnetic field, it's obvious that we are going to have this effect. But this is the magnetic field of this big A. So it's clear that we are going to break translation. And the fact that translations don't commute and we get the charge, it's the same effect as in the toy example, but here we're doing it in field theory. But since we're in the second quantized theory, the Hilbert space has many states with different charges. In states with different charges, the operator Q has different eigenvalues. We use charge for two different senses. One is the charge that we have background density, and the other the charge that sits here. And since we have different sectors, this is an operator rather than a C number. So the algebra, the translation algebra, is completely different. Naively, there is no Q. So the classical physicist does not know that there is such a Q. It's not symmetry that is there for the classical objects. And we have translations in X and Y. And quantum mechanically, the translation becomes discrete and the algebra is extended. So it's totally different symmetry algebra.
Not numbers.
Q is an operator. It's the field strength.
So not part of the problem specification.
It is. With a particle in background dynamical gauge field, little a. So I had a detour in interpretation in terms of big A. Throw it out. We're not interested in this now. The problem as it was defined, there is one dynamical U1 gauge field, little a. Once you have that, it's part of, it has a magnetic field, its own magnetic field, and its own magnetic field leads to a conserved charge. It's referred to as the magnetic symmetry.
The different magnetic sectors contain different values.
That's correct. Different magnetic sectors of the dynamical field, not to be confused with the different sectors of the classical field that I put from the outside, and I told you to ignore for the moment. So this this curly Q as a conserved charge exists even if I don't turn on K at all. Even for K equals 0, I have such a conserved charge. And there are different sectors in the Hilbert space with different values. But right, and that's the case. But when I turn on K, when K is non-zero, the symmetry becomes discrete and the operators don't commute. So armed with this interpretation and with this understanding, I'm now going to present a huge family of models that exhibit this phenomenon. And some of them are models that people studied for other reasons. Yeah? Because when K goes to 0, the reason I got Ti to the K equals 1, so I can't just set K to 0 because K is not a continuous number. The reason I got it is that in the definition of Ti, there was a 1 over K. I think I had it in the previous slide. No, I'm going in the opposite direction. Okay, so if K is 0, I don't have the shift term here. Right, so I don't have this whole thing with the Chern-Simons term is not there, so I have continuous translation. And the interpretation is that T, the conserved charge, is dt to the I, roughly the momentum divided by K. Right, there's a 1 over K. So when I set K to 0, I have continuous translations. Okay, yeah. So in 1 plus 1 dimensions, it's the ordinary theta parameter for A. And in higher dimensions, it's like a theta parameter for each plane associated with time and X. So for each Xi, there's its own theta parameter. And this is what shifts. So when I shift, it follows from, it follows from this formula. When I shift X by a constant, the action is shifted by this amount. So if I put this thing originally in the action, the corresponding theta parameter, which is the number here, is shifted by a constant. So let me generalize it. So we can generalize it in many ways, but one of them kind of is really begs we generalize. The hero of the story was this symmetry that I had, this magnetic symmetry. So we have many systems that have such a global U1 symmetry. Call it a D-2 form symmetry, or just think of it as any conserved charge. So this thing is a current with two indices, and its periods are quantized. And whenever we have that, my story applies. There's a huge class of models that have such currents, such conserved currents. And I would like it to be conserved so that dj is 0. And therefore, locally, I can solve j in terms of some phi, big phi. So locally, big phi is well defined, but globally, it's not. So in our U1 example, the conserved charge was the magnetic field or the electric field, I think in the Lorentz invariant language, and this phi is the vector potential. But there are many other examples, I will soon show more examples, where we have other reasons to have such a conserved current, and there's a corresponding phi. So here are some other examples. The S2 model, usually studied by lots of people in different contexts, in any number of dimensions, that has such a current, J. And if the target space is a T2, 2 torus, we have such a current J. The target space is a Calabi-Yau manifold, we have lots of these J's. So whenever you have a system which has a conserved 2 form, and its periods are quantized, my story applies. So I'm not going to do it in complete generality, and then we'll get examples.
D-2 form is something that couples that D-1A corresponds to a D-.
In this case, big J is a 2 form, no J, no D. So this is uniform in all dimensions. All I need is the conserved current will have two indices. D? Because if the current is a 2 form, the symmetry is called a D-2 form symmetry, because the gauge field has more indices. Yeah, it's confusing because you have to subtract 1 or D minus that, but after a while, you don't get used to it, you just remember. Yeah, I was behind this terminology, and believe me, I couldn't find a better one. And I'm still getting confused all the time. But if I just sit quietly, yeah, I got it right here.
The J is the mod dual of it.
Sorry?
J will be mod dual of it.
Well, dual is depending on how you define a current. So historically, people thought that the current has one index, and the conservation is d mu j mu equals 0. That was the way when I went to school, that's what we were taught. The more modern way is to say that J really has lots of indices. It's a high form. And the gauge field has one index. And yeah, that's the more modern way of saying it. But all this does not change the bottom line. J is a 2 form, or if you change the indices, it is a D-1, maybe D-1 form, if you take the dual. But yeah, believe me, counting this way is less confusing. Sorry? I'm sure I got it right here.
And just to make sure I'm understanding, J in the previous example was D little.
Yeah, here.
Yes.
With the 2 pi's.
Yes.
And I really made sure that the 2 pi's are in the right place. So there are lots of examples of that. But now we can just repeat the same discussion in a more abstract and more general way. We don't need to get to the details. So we have a conserved current J, we couple it to big A. Naively, we can integrate by parts and say that J is d phi, and we can integrate by parts and write it this way. And then we specialize to A, which is constant magnetic field. I'm just going through the same thing, and with PowerPoint, it's easy. I just copy the equations and put it back here. And then I'm adding to the Lagrangian the term proportional to K with big phi. And classically, it's translation invariant, but this phi is not globally well defined. And as a result, I get anomalous translations, only discrete translations, and the symmetry is extended. So this is, now you see that this is really a very, very general story. And let me specialize to one example that people might be interested in. And the example will be nonlinear sigma models. And I mentioned some examples of nonlinear sigma models before that have such a symmetry. So in some cases, we can describe the target space as a gauged U1 with a gauged U1 symmetry. So for example, in the O3 sigma model, we can describe the target space as being S3 and we gauge the U1. This is known as the CP1 presentation of the model.
Is the modification of the algebra would still be with this PITJ equal to e to the power
The charge.
Yj.
Yeah, it's the same thing. You just follow the same discussion.
What is this general language? Uij?
Q is the charge of the current J. So in the special case when the nonlinear sigma model can be described as a U1 gauge theory with some target space, it's not just a generalization of the previous case, it's identical to the previous case because the field strength of the dynamical U1 is this J, which is the conserved current of the sigma model. And we can also specialize to another subcase where the sigma model is a symplectic manifold. If you think this is too abstract, ignore that comment. The S2 target space is an example of a symplectic manifold. And then, first of all, this big phi has a name. When something has a name, it's good to use the name because it's not something I invented. It's the pullback of the Liouville potential to space-time. And also, when we add to the Lagrangian a term linear in phi t, since the manifold is symplectic, all the high time derivative terms, all the terms with two time derivatives are negligible compared to the one time derivative, and we can neglect them and stay with only the one time derivative term. So let's go to a very concrete example, demonstrating all the things I said in the model that many of us like. And that's the model of an antiferromagnet or a ferromagnet. So the O3 antiferromagnet is described in the continuum by the standard O3 nonlinear sigma model. Hundreds of thousands of papers on this subject. This is not, do not deserve any credit for this. And that model has a D-2 form symmetry associated with skyrmions. So in 1+1 dimensions, it's not strictly a symmetry, but there is such a term that we can add, we can write. In 2+1 dimensions, there are skyrmions, and there is a global U1 symmetry. And if we do the same model in 3+1 dimensions, this is a one-form symmetry. Notice always D-2 form symmetry. And it has a conserved charge Q. So now we can just turn the crank and derive all our results. So we turn out background field, and we find a term. This term has a name in the literature, is known as the Berry phase or the Wess-Zumino term. The target space is a sphere, and it can be stereographically projected on the plane, and it's parameterized by a complex field Z. So we just add to the Lagrangian this term, which is first order in time derivative. And let's go to D = 1. In 1 dimensions, we can add a theta term. So this is the nonlinear sigma model in 1+1 dimensions. There is a theta term, so we write theta times this object, right? Theta times that is the term that we can add to the Lagrangian. But now I can study theta, which is linear in X, as I said before, in the same nonlinear sigma model, the same O3 nonlinear sigma model. We can have a theta which is linear in X. Surprisingly, nobody has said that. And I checked it with some of the people who worked on the subject. Take the nonlinear sigma model in 1+1 dimension with its theta term. This model got a Nobel Prize. Many people studied it. And let theta be linear in X. Right. Once you have a parameter theta, why not make it linear in X? And what it does, then you can integrate by parts, and locally you find this term. And this is the term that describes the ferromagnet. So you can think of in the continuum, the ferromagnet is obtained from the antiferromagnet by letting theta be linear in X. Because once you open the door to have theta, you might as well make it linear in X. And then this is the same as the Lagrangian for a ferromagnet.
Sorry, I have not.
Yeah.
If you go back to the previous time, I stopped understanding. Well, it's the Lagrange, is the Lagrangian the relativistic Lagrangian?
Yep.
Del nu Z. And this term here, it looks like the metric on CP2.
CP1.
CP1, yeah, CP1. And so it's like a field, a uniform field strength on it. volume form on CP1. Sorry, could you explain what this
Which formula? This one?
That one.
In
That's Q equals integral. Yes.
Okay, so let's be an arbitrary number of dimensions.
Yes.
Which are the standard relativistic Lagrangian.
Okay.
In fact, you don't even care what the Lagrangian is.
Okay.
The target space is S2. So any two cycle in space can wrap the target space and lead to a conserved charge. People refer to it as the skyrmion charge.
Good.
So this is the current of that charge, and this is the corresponding charge. So
In 1+1, this is the instant charge.
that's correct. So that's why it's a -1. That's why it's a -1 function, because it's not an object in space. It's not an object in space, but it exists in the partition function. Once you have this option, you can turn on theta in 1+1 dimensions. You just say, okay, this is the O3 sigma model. It has a theta parameter. But it's still the effective Lagrangian, the low energy effective Lagrangian of an antiferromagnet. And the antiferromagnet, if you start from a lattice, has either theta equals 0 or pi. But once you broaden your horizon and you're interested in this nonlinear sigma model for any theta, you might as well make theta linear in X. And when you make theta linear in X, what you find is a Lagrangian that you already know about, but in another chapter in the book. This is the Lagrangian, the continuum Lagrangian for a ferromagnet. So from this perspective, the ferromagnet and the antiferromagnet are not two chapters in the same book, but they really describe the same model with a different background field, which is the modern way of thinking about field theory in general. You should view the field theory as a function of all its background fields. And once you have a theta parameter, theta depending on X should be in the same chapter of the book as theta being 0.
Why is that the
Why this is the ferromagnet, that depending on, I don't have more time, I could explain that, but it appears in the chapter of the book which describes ferromagnets. This is known from the 60s or 70s. Yeah, it was analyzed in a lot of detail in the 80s, as I will soon refer to people.
The formula that I'm thinking of that is sort of like the gauge field whose D gives you that shape. The right hand side. Is that right?
You could, but I wouldn't like to think of it this way. So you could, if you think of the model as being the CP1 presentation, where you have an S3 target space and a dynamical U1, then what you said is completely right. But if you integrated out the gauge field, this is some functional of the targets of the fields. And this is a term that you can add to the Lagrangian.
Sorry, this X is beta is linear in X and X is what? It's one of the.
I'm working on a torus. Space for me is always a torus.
And now you get this term by doing an integration by parts.
Which term? So I'm writing this term. This is something that you know very well, right? So you wanted it to be in 1+1 dimension. You wanted it to be the instanton of CP1. So you have such a coupling. Now let's take this coupling and substitute this theta. That's a good thing to do because X is the same as X plus L. And you see that if I shift X by L, it shifts by 2 pi times an integer. So I can do that. So when I do that, I can integrate by parts and locally I get that. There's also a surface term I need to worry about. And you really have to, because the whole story is somebody could say, oh, don't integrate by parts. And then it looks like it's translation invariant. If you don't integrate by parts, there's a surface term you have to worry about. If you do integrate by parts, there's another surface term you have to worry about. But either way, so if you write it, if you don't integrate by parts, and you just have X times this, it looks like you don't need to worry about it. It's obviously not translation invariant, right? Because there's explicit X in the Lagrangian. The confusing thing was if you integrate by parts, it looks like there's no X in the Lagrangian, but this dependence is still there in the surface term.
Then what happens to that?
Well, the model is not translation invariant.
Right, still not.
Yeah, no, by integration by parts, you do not change the symmetry of the model.
Yeah, but somehow you got it.
I started from an antiferromagnet. Think of the antiferromagnet as a name for nonlinear sigma model. And think of the model with this, give it a name ferromagnet.
Okay.
That's not the historical order. The historical order was that the antiferromagnet existed and the ferromagnet, and people worked out the low energy effective Lagrangian.
When you get the ferromagnetic term, you also have the surface term. So
It's all, so what I mean by, so, right. So the way to think about this is that this is an imprecise way of writing the term in the Lagrangian, and the full thing has a plus dot, 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 which includes various surface terms.
Which of those should you call the ferromagnet?
The ferromagnet is the one that makes sense. Only one of them makes sense, and that's the one with the appropriate surface term. That's the only one that makes sense. The others just don't make sense. So the one way to see that is that
if I just added this term in the theory without going through those steps,
locally that would be fine. It would be the same thing, but the action will not be well defined, as I will soon explain why. So imagine you say, don't bother me with all that. Take the ordinary model that I know and love, the O3 sigma model, and just add this term by hand. And that's clearly translation invariance. So what am I talking about? Well, this guy is not quite well defined, because in configurations where Z visits near infinity, this does not decay fast enough. So you say, oh, I have to fix it up. I fix it up and add patches. I have some rule how to go from patch to patch, et cetera, et cetera. And in that rule, you will have to break translation symmetry. So in order to avoid all that, I went through this roundabout way. So one way of doing it is just couple it to a gauge field, and this is just A sub t. Anyway, this is the Lagrangian. And in this case, the target space is actually symplectic, so we don't even need to worry about the second order time derivative terms. They are negligible, because wherever we go in field space, the first order in time derivative dominates over the second order in time derivative, so we don't even need to worry about the second order time derivative.
what happens if you have a target space that's not symplectic?
It's still true, but I'm not allowed to neglect the second order time derivative.
There are still first order time derivatives?
I can add first order. In order to be able to add this first order time derivative term, I need there to be a non-trivial 2 cycle. I need non-trivial H2 with integer coefficients. Or I need to have, once I have that, the whole story goes through. So I take your favorite Calabi-Yau manifold, it has that thing. People don't normally add that because they want to watch it Lagrangian to.
Missing a basic point. So where are you using the fact that it has a symplectic form?
I neglect the two derivative terms. Because if in general you can have some configurations where the first order term does not dominate over the second order term. Imagine you have a potential that rises in all directions except some. So if it does not rise in these directions, you have to go further out, and then the second order in time derivative kicks in. But if it's symplectic, there are no such directions. This form is invertible. There is a whole math that goes there.
You're using some invertibility.
Yeah, but if you don't care about that, keep the second order time derivative and you don't miss anything.
Just make sure it's symplectic form is the Taylor form.
That's correct.
Just simple-minded terms, once the leading time derivative term is a symplectic form, then you have a nice phase space and so on. And
that's correct.
Neglect the higher derivative.
That's correct.
If that doesn't happen,
that's what you need to include. It's exactly right. But the phase space is more complicated because the story with the phase space is true if you're just doing quantum mechanics. So if Z is constant, this is the problem in quantum mechanics that depends only on T. But our problem has X dependence also. In fact, the X dependence is what I'm interested in. So once it's X space, the phase space is much larger because the phase space is maps of space into that target space, right? It's a much larger, in quantum mechanics is a point to the target space, and then it's the same as the target space. But here it's larger. So this is the continuum Lagrangian of a ferromagnet. So yeah. It's a total magnetic, it's a total spin of the system.
And then so you said for theta equal to 0, you have a ferromagnet.
That's correct. So the total spin is 0, right? The total spin.
Oh, the total spin.
The total spin of the system. In the ferromagnet, you know, all the spins point in the same direction. And that's consistent with saying all the spins point in the same direction. So if you look at the 0 mode, and you just look at this term, this is the standard Lagrangian that gives you S2 as a target space. So my time, I went over time. I'm sorry about that. So I'll soon get to a point that I stop.
it's very
Yeah.
sorry. In fact, in this case, to turning on that background gauge field So to say that your linear and theta dependence, is it a magnetic field of the background?
That's correct. Yeah. The magnetic, the gauge field is like theta. We are in 1+1 dimension. So the magnetic field is a zero, the gauge field is a zero form theta, and the term linear in X is a field strength, which is d theta, which is a constant. But these are words. So there's a formula. Theta is linear in X.
Just physically.
I want to relate that to the more general discussion. And in this case, it's actually known since 86 by Haldane that this model does not, in 1+1 dimension, breaks translation symmetry. So the fact that the ferromagnet in 1+1 dimension breaks the translation symmetry is known since 86 with a reasoning which is completely different than the one I gave, but it's exactly the same answer. And Haldane was interested in the model on the lattice. And then he basically said that, okay, the model on the lattice was not translation invariant to begin with. So, and I'm only interested in the model of the lattice, so that's why I that's what I have. It's not translation. I'm saying a stronger statement that if you just wrote the continuum Lagrangian, forget where it came from, it's still not translation invariant. So at this point, I think it's really, I went over time. So
there's no time for us. It's depending on your edit.
Okay, so for me, K can be 3. It has to be an integer. Now, you might be interested in various limits, that the volume is large or K is large. You can study various limits. What I said is true for any K. Nothing has to be large. There's no approximation. That's correct.
Also, just one thing, let's say he's starting from one, will give you the ferromagnet case.
So the interpretation would be that I call it ferromagnet and antiferromagnet, and that is what happens if I start at short distances with some lattice of spins, etc. That's the terminology I use. And in that case, indeed, K should scale like the total number of sites. But the perspective I took here is I write a continuum Lagrangian. I don't care where it came from. And K could be 5. Now, when I said that I can neglect the second order time derivatives, if K is small, then that's not quite right because the expansion parameter is kind of 1 over K, right? So this is really good when K is large and I can really neglect the high order terms. I think, right? So because there's a coefficient K out front. But it doesn't have, for what I said, it doesn't have to be large. Sorry? If you, that's right. But you have to do distances which are kind of roughly 1 over K. 1 over K or 1 over power of K. Yeah. But yeah. But if you keep the higher order terms, and K, you don't take any limit, finite volume, finite K, keep the high order term, that's fine. My only point is that the translation symmetry is not there. Okay, in view of the time, I think I should stop. I will not give you the option. Okay, I'll be nasty. I'll give you what the other slides are, but I'm not going to show them. So you could ask what happens with Netter procedure. If I broke the translation symmetry, what's wrong with Netter procedure? What goes wrong there? I have 2 slides on that. 2 slides on the fact that in some cases, this symmetry comes back as the translation symmetry that we lost comes back as a non-invertible symmetry. This is something that people are interested in. 1 slide on the infinite volume limit. It turns out to be quite subtle. Depending on how you take the limit, you get different answers. There are 4 slides about putting the system on the lattice and see what's the relation between translations on the lattice and translations in the continuum. And I have 2 slides about anomalies, 2 anomalies. There are anomalies on the lattice and in the continuum and how they match with each other. And I did not put slide here, but it's discussed in the paper, how all that is related to the kind of anomalies that Shiraz likes. In fact, the problems that Shiraz should have faced exactly this issue. I came to it through anomalies. That's how I came to this problem. But Shiraz could have asked himself the following question. He studied for the last decade or so dual pairs of theories in 2+1 dimensions, with Chern-Simons coupling and all that, with fermions and bosons, or bosons and bosons, etc. And all these systems had a U1 global symmetry. So you could say, let's couple it to a background gauge field. And let this background gauge field be constant magnetic field. So on one side of the duality, the U1 symmetry is the particle number. It's the particle number. So this is standard magnetic field. And with the standard magnetic field, translation is discrete, and the translations don't commute. If the duality is right, the same thing should be true on the other side of the duality, where it doesn't seem to be the case. So this could be used as another test of the dualities, which seems not to work. And the way it works is actually quite nice because the translations are also broken on the other side. So these dualities were there, and actually there's a hint of that in one of the papers in the appendix. People wrote about these things that for the dualities to be right, something like that has to be true. But this is a much more general story.
But this one of your papers?
No, there's a paper by a large number of authors that I refer to. There's Ashwin, Vishwanath, and Zolotal, and Max Metlitsky, and I forget who else. I think there are a bunch of other authors. They have an appendix. They didn't phrase it in the way I just did. And the Lagrangian was not quite right because there are things that have to be quantized properly, and they were not quantized properly. They were doing it for the fermion duality. But they did say that the translation is discrete on both sides. The derivation is completely different, and I think it's incomplete actually, but the statement is definitely there. But there's a huge number of models, right? There are 3 parameters, N and C, and F and K, and with UN or SUN or et cetera. There's a long list of such models, and many of them have a U1 symmetry, and whenever there's a U1 symmetry, this story applies. So this is a new test of your dualities, and fortunately it survives, and it survives in a highly non-trivial way, because on one side, as always with dualities, on one side it's completely manifest, and on the other side it is subtle. But the subtle thing is what I described here. Yeah.
Once you work in this abstract way, it's clear.
That's correct. Yeah. In a more abstract way, in fact, in the recent paper I wrote that it took 1 paragraph. So what we have is you have a current, we couple it to A is constant magnetic field, and therefore it has to work. Right. So I don't need to check it on a case-by-case basis. Okay, so I think I'll stop here.
Isn't something that takes before starting there's some
The theory is oops. Whoops, what did I do? Okay. Yeah. So K is a parameter of the theory. Yeah, K is a parameter, and you can study the model as a function of the parameter.
From the example that shown, can we think of this from anti-ferromagnet to ferromagnet case as some transition?
K is a discrete value. K is a discrete value, and the model is parameterized by an integer K. And if you're interested in macroscopic systems, then K is macroscopic. And there's a model with K equals 0, where the total magnetization is 0. That's an antiferromagnet. And it's 0 because the spins are like that. And in the ferromagnet, the K is of the order of the total number of spins. Sorry, it's? Okay, that's a parameter that appears in the Lagrangian. Yeah.
Can you take that as parameter and do? Can you ask similar question?
K is still discrete. For fixed volume, we work in fixed volume. K is discrete.
Maybe he's asking what happens if you take V to infinity, K to infinity, and make it sort of that ratio.
Okay, you can do that. So K over V will be, I think it's called the magnetization. the total spin per unit volume is the magnetization. And yeah, depending on the value, you get different answers. But if you take k to infinity, the symmetry becomes zk. So if you take k to infinity, the symmetry becomes continuous. So you don't have the symmetry breaking, but you do have the extension. So the translations still don't commute. So in the case of the ferromagnet, you would say, of course they don't commute because we're in a magnetic field, right? We have charges in the magnetic field. But this is much more general.
Okay, more questions?
The 1+1D anti-ferromagnet. Theta equals 0 is supposed to be the spin 1 anti-ferromagnet. Theta equals pi is spin half. But now you want the theta that stays.
Yeah.
Is there some sort of
Okay. Yeah. Almost. You can describe the model with interactions. So, okay, let me rephrase the question. I was in the continuum. So there are no lattice spins and all that. But you could still have interactions that some fraction of the typical configuration, some fraction of them are anti-aligned, and some of them are aligned, very rarely. So then K would be small. K is the total magnetic field. So it's still not linear in X. Now, sorry, I misspoke. I think what I had in mind was the response to his question. The way what I describe as theta linear in X is what you call a ferromagnet. Theta equals X. So if you're in the continuum, yeah.
I follow what you're saying.
Yeah. So theta equals 0 is integer spin on the lattice. Theta equals a half is half integer spin. And from the continuum point of view, both of them are nonlinear sigma models, which starts their lives is kind of what you can call gapless in the UV, and they become gapped or gapless in the IR. That's anti-ferromagnetic story. Now we go to the other chapter in the book that describes the ferromagnet. In the ferromagnet, it's gapless. In fact, I like to call it very, very gapless because there are lots and lots of states at low energy. Now I'm going to describe it in the other language. The way I would describe it in the other language is there is a theta, and from the lattice I get either uniform theta equals 0 or uniform theta equals pi. But I'm writing the continuum Lagrangian, and the continuum Lagrangian has a parameter theta. In fact, right, so I can study it in the parameter theta, and then let theta be linear in X. And now if I integrate by parts, I find the Lagrangian of the ferromagnet. So the theta linear in X, if you study these Lagrangians of the ferromagnet, you say, I already know this Lagrangian. I've spent half my life studying this Lagrangian. Don't confuse me with another presentation of it. And then this Lagrangian is not translation invariant and say, okay, it is what it is. However, if you spend all your life studying the antiferromagnet, which is the nonlinear model, either with theta equals 0 or with pi or in between, as many people did, then all I'm telling you is that you should have also studied theta that is linear in X, and then you would have found the Lagrangian in the other chapter of the book. In that sense, they're all unified. But if theta is linear in X, you're not surprised that it's not translation invariant, because you see X with the naked eye.
Can the translations be anomalous in the fixed point conformity?
I'm sorry?
Can the translations be anomalous at a fixed point of algebra, where you have some non-conformal?
Well, it's not conformal. It's this Lagrangian of the ferromagnet is not conformal, but it has gapless mode. It has gapless modes. In fact, it has more gapless modes than the typical conformal field theory. It has lots of states at low energy. And in simple cases, like in 1+1 dimensional on the lattice, it's an exactly solvable model. Right, so, and it's not translation invariant. So if you have an underlying lattice, you could say, of course, it's not translation invariant. It was never translation invariant to begin with. But you could ask, typically, when you go to the continuum, you get more symmetries. So you could ask, do we get more symmetries in the continuum or not? And that's actually a very elaborate story, which was one of the slides I skipped. Yes, this was one of the slides I skipped. So you can follow Netter procedure and find the energy momentum tensor. And these systems have two energy momentum tensors. One of them is conserved but not well defined. The other is well defined but not conserved, exactly as in the ABJ story. It's not one loop, as I keep emphasizing. It's just making the term well defined. So when you say that when in the West-Zumino term, the coefficient is quantized, that's not because of one loop. It's just making the action well defined. It's kind of similar.
And just to understand the general take-home conclusion, regardless of dimension, if you have a two-form current, understand? Then you can, then this whole story can play out.
Yep.
You take a background field and you turn on some magnetic field and all.
And you can count +1 and -1 and all that. This is a magnetic field that fills space. Yeah.
Space.
And once you do that, despite appearance, it's not translation invariant.
This is already, it will take me some time to wrap my head around, but once we understand the source story, can you generalize it by replacing the two form with something else?
Yeah, you can generalize it in many ways, but here the idea was that I start from something that classically is Euclidean invariant. So that's what made it D-2 form. So even if I turn on magnetic field, I wanted to at least make it at least naively to be homogeneous. Now, you can also turn on something that breaks explicitly. So once you start breaking, so I already broke Lorentz invariance by turning on this magnetic field, but at least I did not, classically, I did not break the Euclidean symmetries, but quantum mechanically I did. Now, once you open, it's like a Pandora box. Once you started it, you say, wow, might as well. Yeah, no, I'm not, it seems, I'm sure you can. Take any one of these models and do it in one higher dimension then. Yeah. The continuum theory? Well, you could. Well, there's a question of what you mean by coupled to gravity. You can take systems that are not translation invariant and couple them to gravity. This room is not translation invariant, as you can see. And believe me, it's coupled to gravity. But
how can you couple it in diffeomorphically in any way if you don't have a conserved structure?
Well, you cannot. There's a preferred point in space. Well, you will have to put the, yeah, you can, in a way, you can couple it to gravity, but it's not translation invariant. Look at this room. Look at this room. It's not translation invariant. My pointer is here and not here. It's not translation invariant. But I can assure you that if I drop the pointer, it will fall because it's coupled to gravity.
The room has conserved stresses. I mean, if you account for all the matter.
But if you account for everything and everything, this thing is also translation invariant.
You mean the background?
Or if you make everything dynamical, then it is translation because you include also all the couplings.
So the thing that was breaking was the background.
That's right. But
yeah. Fact.
No, but the thing is that in the presentation with the magnetic field, even there it was not obvious because the magnetic field is constant, but it depends. Translation symmetry is broken because the gauge field for it depends on X. But in the other presentation where we just AT, you don't see all that, but it is still there, whether you like it or not. It's still there.
Thank you.